I am Dr. Hiba ZBIB. In this presentation, I will talk about the electrosurgery. It is the use of radiofrequency currents to cut, coagulate, desiccate, or fulgurate tissue. The outline of this presentation are 1. Introduction, 2. Physical principles of electrosurgery, 3. Monopolar technique, 4. Bipolar technique, and 5. Electrosurgical units, or ESU. Electrical units, or ESU, use a high-frequency electrical current to cut tissue and control bleeding by causing coagulation. Coagulation, also known as clotting, is the process by which blood changes from a liquid to a gel, forming a clot. It potentially results the cessation of blood loss from a damaged vessel, followed by repair. Tissue resistance to the high-density current causes a heating effect which results in tissue destruction. Electrical current is delivered and received through cables and electrodes. The concept of radiofrequency electrosurgery must be distinguished clearly from the process of electrocautery, in which the destruction or denaturation of tissue is by the passive transfer of heat from a heated instrument. In electrocautery, electrical current heats an instrument and a clinical effect is realized when the heated tool is applied to the tissues, or heat conduction. During electrocautery, current does not enter the patient's body. Only the heated wire comes in contact with tissue. Current is measured as the flow of electrons during a given period of time. Voltage is the force driving a current against the resistance of the circuit. Resistance, obstacle to the flow of current measured in ohms. Frequency, number of cycles per second in alternating current measured in hertz. In electrosurgery, voltage is provided by the generator. Current is delivered to the tissues through the electrode tip of the instrument. Resistance to current is inherent within all human tissues. The higher the inherent resistance, the greater the voltage needed for the current to pass. If the voltage is increased, or increasing the height of the water tower, and the impedance is held constant, current will increase proportionately. If the voltage is held constant and impedance increased, current will decrease. The simplified circuit of an electrical surgical unit. 1. The switch is the foot or hand switch. 2. The patient becomes the resistor R in the circuit. 3. Flow of electricity is the current. Electrosurgical units, ESU, use alternating current and increase the input frequencies of around 50 Hz to more than 500,000 Hz to decrease the chance of probable muscle and nerve stimulations, which could occur at frequencies below 100,000 Hz. When the electrical current meets resistance, heat is generated within tissues. This leads to cutting, fulguration, desiccation, or surgical procedure. Electricity can have different effects on tissue, dependent primarily on the frequency of current. 1. Electrolytic effect, 2. Faradic effect, and 3. Thermal effect. With direct current and low-frequency alternating currents smaller than 5 kHz, the electrolytic effect dominates. Ion migration takes place in the tissue. Positively charged ions travel to the negative pole and negatively charged ions to the positive pole, which give us electrolytic damage to the tissue. When alternating currents flow through biological tissue with a frequency of up to 20 kHz, the Faradic effect occurs. Currents within this frequency spectrum stimulate nerves and muscle cells, which can lead to muscle contraction. In high frequency, this effect is undesirable, as muscle contractions are painful and possibly even dangerous for the patient and are hindrances for the surgeon. Hindrances for the surgeon. This stimulus effect peaks at frequencies between 10 and 100 Hz, as we can see in the figure. Nerve and muscle membranes are not sensitive to the very short duration pulses characteristic of the high frequency. The energy is converted into mechanical energy as the cations and anions rapidly oscillate within the cellular cytoplasm. This mechanical energy is converted by frictional forces into thermal energy that in turn results in elevation of intracellular temperature. The basis for all electrosurgery is the thermal effect, which is caused by electric current flowing through tissues. Physicians use thermal tissue destruction to cut or coagulate tissue in the area being operated on. The frequency used for electrosurgery must be sufficient to cross the tissues but without activating the muscles. Such case would cause muscles contraction, preventing the surgeon to work, and it is likely to cause the patient's heart to stop. Electrotomy or cutting. High-frequency alternating current can be used to rapidly heat the target tissue to temperature above 100 degrees, so that vapor pressure explosively rupture the cell membrane. The sum of many small cell explosions creates a cut. Rapid heating of tissue massively increases the vapor pressure, leading to the explosive rupturing of the cell membrane. Coagulation. The tissue is heated relatively slowly by high-frequency electric current, such that intracellular fluid and extracellular fluid vaporize and cause the tissue to shrink. This leads to a coagulation of tissue area and a shrinkage of tissue. No explosive vaporization of tissue. The cell membrane remains intact. 1. Monopolar or unipolar electrosurgery refers to the surgical instrument having only one electrical contact surface or electrode. 2. Bipolar electrosurgery refers to both electrodes being contained within the surgical instrument itself. 1. With monopolar electrosurgery, the patient forms a major part of the electrical circuit. 2. An active cable from the electrosurgery unit carries current to the active monopolar electrode. 3. Current then spreads through the tissue to be collected and returned to the electrosurgery unit by a patient plate electrode attached to the patient. 4. The patient plate electrode is also known as dispersive, neutral, passive, or return electrode. And 5. Radiofrequency oscillator 300 kilohertz to 3 megahertz. Active electrode used for achieving desired surgical effect or small contact area. Dispersive electrode, return electrode at which no electrosurgical effect is intended, or large contact area. The contact area of the two electrodes differ greatly from one another. The contact area between the patient return electrode and the patient's skin is large, which means that the current par area or current density is fairly low. The active electrode, on the other hand, has only a small contact area and the current density is consequently very high. Electrodes are connected to the radiofrequency power generator. Active electrode, small size, many millimeter in thickness, 1 millimeter, and wideness till 10 millimeter. The figures represent active electrode for coagulation and active electrodes for cutting. Dispersive electrodes are almost always designed with an adhesive to facilitate continuing contact with the patient and prevention of a clinically significant local thermal effect. However, if there is partial detachment, the current density will increase and the dispersive electrode can become active and capable of creating thermal injury, often called a burn. The bipolar technique integrates both electrode, the active and the return electrode, in a single instrument. This means that the flow of electricity is confined to only the space between the two surfaces of the instrument. No remote dispersive electrode is needed. This means that the current only flows through a very limited area of tissue between the two electrodes. Tissue damage is theoretically confined to only this direct space. The bipolar technique is a safer modality. We have first the generator, then the active electrode, then the patient, and then electrode tips, and finally the generator. Advantage of the bipolar operating technique. 1. Current flows through the tissue between the two electrodes, that is, through those areas where the effect is desired. 2. The danger of inadvertent burns to the patient coming into contact with conductive materials is negligible during an operation with bipolar technology. 3. No strain current, 4. It has reduced influence on cardiac pacemakers. It was assumed that once the current entered the patient's body, it would return to ground through the patient return electrode, but electricity will always seek the path of least resistance. When there are many conductive objects touching the patient and leading to ground, the current will select as its pathway to ground the most conductive object, which may not be the patient return electrode. Current concentration at this point may lead to an alternate site burn. Why alternate site injury occur? Current delivered must return to generator. Current exit at any conductive object can cause injury. Precaution: patient should not be in contact with any objects with high conductivity, example metal. The thermal damage on the level of passive or earthed electrode has nowadays become rare since the modern generators use insulated circuits able to continuously monitor the return current. Isolated electrosurgical systems. Electrosurgical current from isolated generators will not recognize grounded objects as pathways to complete the circuit. Isolated electrosurgical energy recognizes the patient return electrode as a preferred pathway back to the generator. By removing ground as a reference for the current, the isolated generator eliminates many of the hazards inherent in grounded systems, most importantly, current division and alternate site burns. The original systems were ground referenced, meaning that the ground was an inherent part of the circuit. They depend on the ground to complete the circuit, a circumstance which brings into play the opportunity for current diversion through any components of an operating room table. All contemporary electrosurgical systems use isolated circuits, which means that the ground is excluded. Tissue effects, which can be achieved with generators, can be roughly divided into three basic groups: cutting, fulguration, coagulation or desiccation. Electrosurgical cutting divides tissue with electric sparks that focus intense heat at the surgical site. By sparking to tissue, the surgeon produces maximum current concentration. To create this spark, the surgeon should hold the electrode slightly away from the tissue. This will produce the greatest amount of heat over a very short period of time, which results in vaporization of the intracellular contents of the tissue. Electrosurgical fulguration coagulates and chars the tissue over a wide area. Since duty cycle is about 6% less heat is produced. The result is the creation of a coagulum rather than cellular vaporization. In order to overcome the high impedance of air, the coagulation waveform has significant higher voltage than cutting current. The term fulguration refers to a superficial tissue destruction. This is undertaken by passing sparks from a needle or a ball electrode of small diameter to the tissue. When the electrode is held near the tissue without touching it, an electric arc is produced whose heat dries out the tissue. Electrosurgical desiccation occurs when the electrode is in direct contact with the tissue. Desiccation is achieved most efficiently with the cutting current. By touching the tissue with the electrode, the current concentration is reduced, less heat is generated, and no cutting action occurs. The cells dry out and form a coagulum rather than vaporize and explode. The crest factor is an important parameter. It describes the relationship between the peak value and the effective value of an alternating electric current, and thus indicates how strongly a current is modulated in its amplitude. The higher the crest factor, the more pronounced the coagulation effect. The lower the crest factor, the greater the cutting effect. Depending on the appearance of the cutting surfaces, a distinction is made between a pure cut and blend cut. For a pure cut, where the cutting surfaces don't show any discoloration as a result of the heat effect, an high-frequency current with a crest factor of 1.4 is used. For a blend cut, where the cutting surfaces show a brownish discoloration, an high-frequency current with a crest factor of between 2 and 4 is used, depending on the required degree of coagulation. A current with a crest factor higher than 4 no longer allows the satisfactory cutting. For cutting modes, it has a continuous waveform. Much lower voltages are required to achieve tissue vaporization because it's continuous. It creates higher tissue temperatures in a shorter time, leading to explosive vaporization of intracellular contents. For the coagulation mode, it doesn't have a continuous waveform. Much higher voltages are required to achieve tissue coagulation and the production of less heat, forming a coagulum as the tissue temperature rises more slowly. Electrosurgical generators are able to produce a variety of electrical waveforms. As waveforms change, so will the corresponding tissue effect. Using a constant waveform like CAT, the surgeon is able to vaporize or cut tissue. This waveform produces heat very rapidly. Using an intermittent waveform like coagulation causes the generator to modify the waveform so that the duty cycle or on time is reduced. This interrupted waveform will produce less heat, and a coagulum is produced. A blended current is not a mixture of both cutting and coagulation current, but rather a modification of the duty cycle. As you go from blend 1 to blend 3, the duty cycle is progressively reduced. A lower duty cycle produces less heat. Consequently, blend 1 is more effective at cutting with minimal hemostasis, whereas blend 3 is less effective at cutting but has maximum hemostasis. ESU is the most hazardous device used on a daily basis.